introduce Dr. Steven Schellenberg from San Diego State University's Department of Geological Sciences. He was requested to come back and give another talk about the geology of the Point Loma Peninsula because y'all enjoyed his talk so much the first time. So I'm really excited because I wasn't there during the first talk, but I'm super excited to get to hear from him today. So I'll hand it over to you.
Thanks very much. I think I was actually invited back because I borrowed a bunch of money from some of you. You're probably trying to get it back from me, but it's great to be back. Thank you for coming. Thank you for all that you do here at the park. It's really appreciated. So it's my pleasure to try to just give you a very brief overview, and there's going to be a lot of content here, and it's okay because I'm going to give you all these slides if they're useful to you, and hopefully they will be. The other thing I'd suggest, if you don't have one already, you probably do, but this is really nice resources at the bookstore. This is my 4th copy I just bought, so I'm not loaning it to any of you. But I would really suggest it. And the chapter in here by Pat Abbott and Tom Rockwell, both in my department, is really nice overview and kind of covers a lot of the same material. So it's a pleasure to be here. This is a great addition. I've been coming to the park for years and years. I'm not sure when this showed up. I'm trying to remember, but it's great, and it's really a very concise. Whoever put this together, summarize it to the very key points. So I think it was kind of a 3-part play. And what I want to do today is kind of unpack that a little bit to give a little more background, so that when you're getting questions in the intertidal zone, maybe you feel a little more comfortable with the context. I'm always happy to answer any questions after the talk or anytime. Just email me. Happy to talk to you all. I'm going to try to come out during the early November tides, just so we can see rocks together if you're there. So, geologists work with geologic maps, and there's always a lot of information in maps, but it's sort of our way of writing everything down graphically. And when we think about Point Loma, here's the intertidal zone right here. We're up here in the visitor center. There's a bunch of colors here, and those colors usually mean like a certain kind of rock, some kind of material that's left behind in some way. What we don't have is what's missing. There's always something happening through time. It's just whether it's recorded in rocks or not. So I'm going to sort of go through and talk a little bit about this, starting with the Point Loma Formation, which is the oldest. When you're in the intertidal, you're standing in the Point Loma and on the Point Loma Formation. Then the Cabrillo, which is what you drive down through to get to the intertidal zone. And I'll talk a little bit about the sort of big time when there's nothing here in terms of material. It's very much an erosive interval or non-depositional interval here. And then the very top part is what sort of happened relatively recently, really through interaction of tectonics and regional tectonics and sea level, leading to erosion into the landmass and what is left behind. So sort of 3 parts to the play. Here's the first part. It's that first panel. The second part of sort of uplifted erosion. The third part of some deposition. So here's that first slide. It's basically this first part as it's shown here. In the initial deposition, when you're in the intertidal, there's really fine layers that you look and have exposed in the sea cliffs, and that you're oftentimes standing on, unless you're standing on cobbles and sand that are currently being deposited there. So let's talk about what those are. Those sediments were laid down back in the Cretaceous during times of the dinosaurs. If you could have a Google Earth back then, this is what the Earth would sort of look like in terms of plate tectonics. Here we are. This is the Western Interior Seaway. There's what Florida would become. I'm from Florida, so I could say I kind of like it better underwater personally. So you can see the Atlantic is very small. And there's a lot of stuff going out here, but basically if you were to go back in time, all along our coastline, it was what's called a convergent plate boundary. Much like we have the Cascades to the north of us today, we had subduction going on all along the coastline and volcanic ranges all along the coast here. And you can sort of see that, and I'll show that a little bit later on. But that's what was going on. If you could be standing out in the Cretaceous Ocean and drain it away and look towards what is Point Loma, now it would look kind of like this. This is a shot. That's a tire. Those are tires messing up my outer fan right there. But this is a very small scale kind of model. The great thing about geology, you can see the similar processes at very different scales. So if you could drain the ocean, it would look something like this. You'd have sort of this would be the shoreline up towards here. And at the time here, there's a very large complex of submarine fans. Much like fans here, where you have some sort of high point, and sediment underwater is being transported down And if you can sort of look at this, you can divide any of these fans. You can see this. This is, for example, a fan in Death Valley. So whether it's above water or below water, but this would have been below water, which most people think like, wow, how could that happen below water? Well, this stuff's got to settle somewhere when it comes out into the ocean. So typical fans, here's the sort of shoreline, if you will. Oftentimes there's this outermost fan. This is where the really fine stuff is settling out after it gets deposited out there. And then a middle fan, which we'll talk about, and then an inner fan. And you can see up here towards the top, they're actually, you think of this as all being deposition of sediments, but you're also having erosion in these little channels. This is happening underwater. And I'll show you how this happens. So even though it's underwater, you think of stuff settling out, you can also have flows that actually erode underwater. That's how a lot of our submarine canyons are formed. So this is just a little sort of a mock thing here. There's something from the air, so you have similar features. And so as the sediment's coming off of land, being eroded off and deposited, it's going to start to do something called prograding. That's a really fancy word for stuff getting dumped into the ocean. So if you think about the colors here I'm using for this sort of light tan for inner fan, brown for middle, and black for outer, if you think about it, what will be happening here is sediment would be starting to stack on top and prograde out, okay? And what you've noticed is starting to happen here is that this middle fan environment is starting to stack up on top of the outer fan. And the inner fan is starting to stack on top of the middle fan. This is called progradation. This is how deltas form. And this will just keep happening as long as there's a sediment supply and deposition going on. Well, the ones that's happening is you start stacking these environments that are adjacent to one another vertically. And that's what we have here in Point Loma. That's what we're looking at most of the time. They're given names here. What we're in the intertidal is called the Point Loma Formation. Those sediments are basically represent an environment of an outer fan. And as you go up a little bit higher, there's sort of a middle fan environment. And the sediments tend to get a little coarser as you go up. So just to show you what this looks like, hopefully this will work. These sediments are deposited largely through turbidites or turbidian currents. And what happens is you'll have some sort of event, maybe an earthquake or a big storm or some sort of disruption up on the shelf, and you'll mix sediment and water together. And that mixture is more dense than the surrounding seawater, and it will flow downhill just like you're seeing here. Notice how this sediment-rich water is just hugging close to the seafloor, and this is a tank, and flowing out. And what they've done, you could just do this over and over and over again, and as it slows down and the energy decreases, the sediment settles out, and you get these layers upon layers upon layers. Well, this is exactly what you're looking at. Oops. I think I have to go manually through this part to get out of it. That's what you're looking at right here on the sea cliffs. So zooming on the intertidal zone, these really finely layered sediments that you see exposed, those are layer after layer after layer of episodic sedimentation events coming in, being deposited out on the outer fan. Millions and millions of years ago during the time of the dinosaurs, and being preserved. And you can see it all over the place. What happens here? One of these little events, what do you think would settle out first if you had a big mixture of sand and clays and little cobbles and a really big mix?
Probably larger stones.
Yeah, the bigger stuff settles out first, right? And so what ends up happening, each one of these events will tend to what's called a turbidite. Coarser stuff at the bottom, and it gets progressively finer. One of the biggest basal layers that you see is this layer right here. That rock is no longer there. Well, it's just down here now. So this is one of these really thick basal layers of sands or lens, probably could represent a single big event, okay? Interpreting these uniquely is sometimes difficult, but there's no doubt you can see very fine sort of coarsening, what are called graded beds, where you have a little layer that's sort of coarser down here and gets progressively finer, and then gets coarse again. This represents a separate depositional event, so layer after layer after layer. So a very common sort of pattern.
Could you explain again how those big rocks got there?
Yeah, I'll talk about the big rocks in a second. The big rocks were not there at the time.
Okay.
So these have all been eroded down and deposited from up high. So I'll talk about that in a minute.
All right.
That's a great question, because most of the intertidal stations that you look at here are on these big rocks, right? And I was thinking about that earlier. I was talking about this, some interesting patterns there to think about. So if you've been around in those rocks, stepping around, you may have seen some fossils within them. One of these fossils you'll see is a sort of weird collection of sort of like a broken dinner plate syndrome kind of thing. These are remains of very thin-shelled giant clams called inoceramids. They went extinct at the end of the Cretaceous along with the dinosaurs. But you're looking at their shells preserved right along the surface, and you can see a bunch of these within the bedding plains.
How big can they get?
I've seen, like this, maybe bigger. I mean, the ones around here are about, large Steven-sized dinner plates.
Now, is that the shell that you're
Yep,
saying?
they're extremely thin. They're extremely thin-shelled bivalves or clams. They probably were no about thicker than this. The shells are pretty thin. And you're just looking at the preserved prismatic layer of the shell right here. And so you just have it looks all broken up. You've lost this sort of nice outer layer, but you have, I think it's the prismatic layer preserved. You also have trace fossils. So this is the interaction of organisms with the soft sediment. They were in the sediment when it was soft, back in the Cretaceous, interacting with it. So this is two types of burrows you can see. This is sort of reconstruction, sort of a shrimpy, crustacean-y kind of thing. And this is a burrow that it left behind where they actually lined the burrow, basically spitballs all around. So this is a dwelling burrow that's subsequently gotten filled in. And then you also have unlined burrows, like that one right there. Okay? So you'll see these patterns all over. They're preserved in the rock and now exposed in cross-section or surface, exposed surface layers. You also have some really interesting ones like this called Scolicia. These are all given names because paleontologists have a lot of time in their hands, I guess. So it's a pattern where there's this weird kind of shape, almost, you see it over and over again, kind of what's called a backfill. And these things were probably most likely, because we can see them today, produced by infaunal echinoids, or sea urchins. Sea urchins you think of being on the surface. They can also live infaunally, just like sort of sand dollars do partially infaunal. And they would actually cruise around through the sediment, sort of moving the sediment grain by grain from in front of them to behind them. And they would produce this pattern as they backfilled behind them. So the space they were in was relatively small, but they were producing this pattern right here, this backfill. What you see is an erosion through that, and you can see the pattern. And these are pretty common and pretty cool. So there's a lot of interesting interactions there to try to interpret and understand. So that's the Point Loma Formation. That's what you're standing on for the most part when you're out there. It's all those thinly bedded layers. And it's relatively soft sediment, right? As you well know. You've seen the effects of that lately. Higher up above it, sitting on top, is the interfan sort of environment. That's what's known as the Cabrillo Formation. When you drive down, you're driving through that upper part of the fan as it's preserved there. Now remember, just looking at a cross-section through it, most of it's been eroded long ago. You're looking at just the vestiges of what was a very large system. And you'll see things like channel deposits here. Think of this as one of those channels at the top of the fan that you saw where the biggest rocks get there, but there's not enough energy to take them any farther. Just like a stream channel has the biggest rocks at the bottom. Okay? And stuff just gets stranded there, and you deposit more on top of it, and now you've been eroding back. We'll get to the erosions thing. Okay, that was a big part of the story. The second part, as you say here, seismic activity pushes sediment layers up. This is probably in 1,000 meters of water or more where all this was happening. We have a very long interval where there's not much going on here in terms of deposition, at least preserved. In this region, we have a lot of, over this long interval of time, after the deposition of these rocks, mainly erosion, or at least non-deposition. So this is the uplifting part of the story. It's a little geology joke, as we're lifting sediments up out of the seafloor. I know, it's pretty bad. So there's a lot of rock missing here. No time is missing. The time is just a little layer of nothing, right? But we don't have any material recording that for the most part. So what was going on then? Well, I'm not going to run a geology class. Many of you have probably heard about plate tectonics. As I mentioned, all along our coast, we had what's called a convergent plate boundary, where we had a plate being subducted beneath North America, or what was the North American plate then, a lot of volcanic ranges. And just to show you the kinds of stuff that was going on and why we have such a poor record here is that there was a lot of activity in terms of tectonics going on. So this is from 80 million years ago, so a while after in the Cretaceous, after the deposition largely of the Point Loma sediments we were just looking at. This is a reconstruction based on lots of evidence for what we think was happening in terms of tectonics. Here's the coast of what was then North America, continental crust. I'll just play it here. This is a spreading ridge right here, and another spreading ridge. And there's all kinds of crazy stuff going on here that your geologists should ooh and ah this the whole time. But notice how over time it looks more and more familiar. This is basically the LA Basin in San Diego here. There's Baja starting to form. And what you'll notice right up here is the only place where we now have subduction going on. That's the Juan de Fuca plate, one of my favorite plates to say. So just to watch that again, you can see how basically what was going on here, we were subducting spreading ridges here. And then once this hits, the whole sense of motion starts to really shift to one of transforms, right? Today, that big transform boundary we call the San Andreas Fault. And we're pretty close to it. So it's still happening today. So if we zoom in what we see today, now there's that plate boundary, there's the Juan de Fuca plate right there with subduction. This is where the Cascades are today, active because of subduction and volcanism. But mainly we've got the San Andreas Fault system. We call it one fault, but if you zoom in, it's really a network of faults, almost like braids in a rope. Here's a big San Andreas. Here's LA, that small suburb to the north of us. Here's San Diego. And right through here, the sense of motion, we're basically, whenever there's a big earthquake event, the net motion, even though it varies from place to place, the general motion is the Pacific plate moving northward, or at least northwestward, compared to the North American plate. Okay, that's a typical sense of motion. I want to zoom in even more to get us to right back to where we are locally, looking here in San Diego. What's the local expression of that? And the local expression is what we know as the Rose Canyon Fault. So how many of you have driven up Rose Canyon before? You know what this road is? Yeah, it's basically 5. Isn't it convenient how all the canyons fall where we put interstates? Because it was the last thing we built once we figured out flood control, right? So, and hospitals and schools, places exactly where we want to build these sorts of things. So the Rose Canyon Fault, this is La Jolla, basically Mount Soledad. Here's that geologic map I was showing you here down to Point Loma. And if you're standing on Mount Soledad looking south towards Point Loma, you're looking from one high to another high. So what's happened over time here that's helped with some of this uplift, at least in recent time, if you were to cut through from the north all the way through Mount Soledad, through Mission Bay, back up through Point Loma, like a cake, and sort of look at it in cross-section, what you would see is this. You'd be on the high here, taking a picture, right, towards Point Loma. And these sediments have basically been pushed up in what's called an anticline, slowly deformed over time. Almost imperceptible to see in direct scale, but you can see these slight angles that are in the sediments. And on longer scales actually measure out, this is really compressed and vertically exaggerated so you can see it, but it forms a high, this is called anticline. And then from Mission Bay is a syncline where the sediments have been deformed downwards, and then back up to the Point Loma anticline. Okay, so this has helped expose those Cretaceous sediments today that we see. We're part of an ongoing process, and this is what happens next time we have an earthquake. It'll be uplifted a little more. So that's part 2 of that screen, right? Basically, how do you get stuff from the deep sea in the ancient times back up to the surface? A lot of stuff, but mainly uplift and erosion. Well, what's the rest of the story? The part 3 here is this dance of time, or dance through time of uplift, as I just mentioned, and then also coastal erosion, which is something all of you are thinking a lot about with the sea caves collapsing and all that, right? So, as I mentioned, here's that blue, all this blue stuff right here, Point Loma Formation, that's all that Cretaceous stuff exposed. And Cabrillo Formation, a lot of it is exposed up here, but one thing to notice is there's also this orange stuff. What's all that? Well, this is what's known as the Bay Point Formation, all this sort of orangish stuff here. and it's relatively young. It's the last 125, 85,000 years most of that was deposited. So, but it's a weird place. Like, why is there really old stuff, really young stuff, back to really old stuff? And this is where we have to think about the superposition of, okay, if you cut in and erode into land and deposit new sediment on top of it, and a little low spot, or at least a stable spot, it'll produce that kind of pattern. So let's see how that happens. How do we get this? So sea levels change through time. It's gone up, it's gone down. We've had really high sea levels, we have low sea levels. Just to get you oriented, this is about 250,000 years ago to today. Here's modern sea level, 0. We just set that as 0. And we know through multiple lines of independent evidence that sea levels change through time. What do you think is a big driver of that? What's a big way to change global sea level?
Ice melting, glacier.
Yeah, ice, right? If you look at these glaciers, look soon because they're going fast, right? Almost all that water comes from the ocean. It evaporates off through the water cycle, and disproportionately more is frozen on land than returns back to the ocean. Over time, you grow big ice sheets, sea level has to fall. So here we are today with a sea level of 0. Last glacial maximum down here, about 15,000 years ago, 30,000 years ago. But we've had other times when sea level's been higher. About 125,000 years ago, sea level was slightly higher than this today, from which you can infer, well, maybe there's even less ice sheets, right? So we're actually really interested in this interval to try to understand what maybe a warmer Earth looks like. A lot of people are interested in that. But the point here is that sea level goes up and down through time. So let's keep that in our minds. Let's also keep in our minds that Point Loma is slowly being uplifted on geological timescales, right, through these tectonic forces. So if something, sea level going up and down, and then Point Loma being uplifted slowly. Well, what do we have today right now? If you let sea level just sit relatively stable, and you let the land sit relatively stable, there's a lot of energy coming in from the ocean, right? You've been out there probably during these times. And what tends to happen is you erode in and you get a wave-cut terrace or wave-cut bench. It's basically intertidal. There's your sea cliffs exposed. This is just from a typical oceanography book. So very classic pattern. You erode in, you form sea cliffs, those sea cliffs fall, you continue to erode in, and you might get to some sort of steady state there eventually. But you've created a really flat, sort of notched area here, right? This is called a wave-cut platform. Really creative, right? Wave-cut platform. Even I understood that when I first read it. It's a platform cut by waves. Got it, right? And this can produce all kinds of features, many of which you see here, and we'll be dealing with or trying to deal with, right? So for example, today you might start out with a sea cave. That sea cave, if it goes back far enough, you follow some sort of fracture or instability, some of it could collapse, you create a blowhole. Well, you continue to erode back, and all of a sudden you've got an arch, where the cave is really now so small that you don't even think about it as a cave, you think about it as an arch. You flip it in your head, right? But it probably started as a cave, because it was, you had to really go into it. And now the cave is really short, so now it's an arch. Our little dichotomous brains are interested. So there's the third sort of thing you might see. And then once that arch collapses, you can have a sea stack out here. So these are all related. You're looking at snapshots of what is an erosional process for the entire area. And you can see these examples. Like here's a little sea arch right here. It's like a little bit north of the regular intertidal access area instead of going south and north. Here's a big erosional drop right here. Here's one of those turbidites we're breaking along these fractures. And here it is in real time. So it's a great book. Kuhn and Shepard, 1984. Basically, these guys are around forever, took lots of pictures in the same place. Creatures of habit, I guess. But what you can see, this is 1938. This is a sea stack with a sea arch in it. Here you see it's gotten bigger by 1946. That sea arch right there is collapsed. So this is the span of, what, according to my math, 8 years. And then 1968, well, that one's completely gone. And this one's now just a little nub. So this is an actively eroding area. So just keep these two things in mind. Sea level going up and down, and waves wanting to erode into the land. So those two ideas. So what I'll do now is put into sort of a dynamic concept. But think about for a minute. Let's say we could zoom in to this little record of sea level. Well, it's going up, right? It's rising, sea level is rising, but it's rising at a decreasing rate, right? You're starting to have it slow down, right? It's going to peak, and then sea level is going to start to fall at an increasing rate. Does that make sense? So rising and decreasing to the point where it's stable for a little bit, some amount of time, and then we'll start to fall as ice sheets wax and wane. Okay. So here's a little conceptual model. I hope it works. If not, this was not my idea. It's genius. Totally came up with it on my own. All right. So think about this little model. Think of this as the sea level rising at a decreasing rate. So it's rising, very steep here, but slowing down and sort of flattening its rate to a point where there's no change right here in sea level. And then it starts to fall. Ice sheets growing, ice sheets decaying away. And this is just absolute elevation. Think of that as, vertical thing, right? So you could splice this thing up into three parts. Oh, let me also add, now think about you standing on the shore. You can live a very, very long time. You standing on the shore, and you're feeling the land slowly uplifting, right? And let's just say it's a constant uplift through time, right, on average. Just slowly you're getting uplift, which is what we know is happening here. So we put two things on top of each other. Now let's split this into three time intervals. There's going to be a time right here, this interval 1, where sea level's rising faster than the land is lifting up, right? So if you were standing on shore, sea level would be rising for you, right? If you had a house there, you'd be worried. Okay, so that's the first interval. This would look like there's the land, sea level's rising much faster than the land is being uplifted. But right here, this interval 2, right in there, sea level and land are moving up at about the same time, which means if you're watching the ocean, it wouldn't seem like it's rising. But what's definitely going to be happening? Erosion. You're focusing the energy into a very specific spot. What would we call that? A wave cut platform, like that super creative term, right? It's a platform cut by waves. Now, what would start to happen over here? What's happening now? Sea level's peaked. Sea level is now rising slower than the land, right? And now it's actually starting to drop. So what's going to happen in this interval that you cut into right here is it's going to keep being uplifted, even though sea level's falling. Right? And so what happens to stuff that has a flat spot? You can have sediment erode down onto it, and that's what you do right there. So you might right here, this would be an ancient intertidal zone, right? And then as it's lifted up out of the intertidal, you might have some sediment erode off of the land and be deposited on top of it. So that, my friends, is exactly what we are on in many ways when we're down there. Here we are right here. This entire area is an old wave cut platform that's been lifted up. It's called a terrace. This represents sort of two intervals, 125,000 years ago, when sea level peaked, and also 85,000 years ago, when sea level peaked. During those two times, land and sea didn't shift very much, and erosion went in. But then what happened? Sea level fell, sea level came back up, but during that whole time, this region was continuing to be lifted up higher. Okay? So two things going on. Usually we like to have just one thing changing. But to produce these, you need to have two things changing. So if you were to cut through, we're about right there. If you were to slice through, I'm not advocating this, or people, I'm not advocating cutting through Point Loma, but if you could slice through it, this is what it would look like. It's the Pacific right here. Here would be where we are. There'd be San Diego Bay. This is all pre-Quaternary. This is the Cretaceous stuff. These are people that work on, recent stuff. They don't care what it is, but it's the Cretaceous cool stuff. So it's all there exposed. But what we have is this wave cut platform and this wave cut platform. That one that's a little bit higher was formed about 125,000 years ago during that high stand. It's about 6 meters above sea level today. Sea level back then was, people are estimating around 5 meters. So it's been, there's been some uplift here and there. But we also have on top of it, cutting into that one, is a younger one. Okay, so there's actually 2 wave cut platforms. This one, which is older, and this one, which is younger. But sea level basically didn't get quite as high. So it's lower, relatively speaking. So this stuff right here, and then you have on top of it all stuff called talus and non-marine sediments. That's all that buff-colored stuff that people are walking on and slipping on, and you're trying to keep from eroding. Good luck with that. And so when you put it all together, these 3 parts, here's part 1, that Cretaceous submarine fan. Here's part 2, basically uplift and removal of material largely. And part 3 is this formation of these terraces that produce a really weird thing. It would look like, wait, we go from, you always learn, the oldest stuff's on the bottom, right? Which of course, it's true. It's just here you think, well, that's sea level, I'm going to higher elevation, so how can I go from Cretaceous rock to relatively recent rock back to Cretaceous rock? It's because you've cut in and dumped a bunch of young stuff. Okay, I didn't pause it. So here's the take-home message. When you're out there looking at this environment, you're looking at an incredibly complex history. Right? So this is where I sit with my wife when we come, when we're too lazy to walk out there, and watch people do stupid things here, and you all try to stop them. Right? But if you zoom into that spot, right, here's a classic spot. This is almost all of this is exposed Cretaceous outer fan sediments. You're standing in the modern wave cut platform. All these sediments, if you look in here, you can find the borings, all that kind of stuff. These are made by marine organisms boring into the rock, right? In the rocks you already know. So it's littered there. But if you look right here, you can find those same borings. Those borings are from 85,000 years ago, when that was the intertidal. So when you're driving down through a fan that was deposited 70 million years ago, and you're driving through not one, you're not really driving through 3, because then your car would be in the water. You're driving through largely 2 ancient intertidal zones. Okay? And so this is the one that so 3 different time intervals. Cretaceous, back in the dinosaurs, about 125,000 years ago, and 85,000 years ago, you can lump those together. That's when this stuff was being cut. You can just sort of lump those together. And then today. But 2 fundamentally different environments. The deep ocean, more than a kilometer deep, and right where the land and the sea meet. So here's a cross section if you head out, just to put it all together. There's that Point Loma formation, outer to middle fan. The inner submarine fan that was flowing out over it, back in the Cretaceous. Then you have cut into it what we call the Bay Point Formation. And so it's a really thin layer here. Technically it's that part, but they kind of lump in this relatively recent stuff that's gotten washed down in. That's the Coast Guard station right there. But that is the ancient intertidal zone right above the modern intertidal zone. There's another one up here, it's called the Linda Vista Formation. It's a very old terrace. It's really hard to find. I've never found it myself. I think if I were to find it, the rangers would tackle me because I'd be out there in the brush. But there are exposures of it on this spot. It's sort of, if you notice, this is kind of a flat area. They've done some, shall we say, leveling in the past. But one reason why Point Loma is relatively flat, you've captured one of these relatively old terraces right near the top. And it's a relatively durable surface. So I'll stop here because I'm running over. But so when visitors come in, right, this is sort of the experience they'll oftentimes have. They're going to walk on the Cabrillo Formation, right at the top of it, and maybe the Linda Vista Formation covered up by asphalt and all that good stuff around the visitor center where we are right now. Many of them will drive down through an ancient submarine fan, which is the Cabrillo Formation, this stuff, looking out at the ocean, whereas every geologist is looking at the rocks. So I like to look at the stats for people that drive off the road. They're almost all going to be geologists. And then they're going to park over here on the Bay Point Formation, or the fill. They're going to stroll across that ancient marine terrace, climb down the rocks into the modern intertidal, and look back. So, a couple slides to wrap up. What now? That was all past. What about future? Well, we've been paying attention. This is back in the last glacial maximum, last ice age. That's a little squirrely guy from Ice Age. I forgot his name. We have great records of the history of sea level rise. Here we are at 0 right here. Sea level was about 120 meters lower, back around 22,000 years ago. And it's been steadily rising as the ice sheets melted. Total sense. Right here is the start of the Holocene. The Holocene has been an interval of relatively stable sea level, coincident with the development of almost our entire civilization. Coincidence? I think not, right? There's lots of evidence this is why we've stabilized and developed as a society. Here's our local uprate. We have about maybe 10 centimeters here per 1,000 years is the estimate. So I just laid that on there. And what you see here today is that the average uplift rate is about what the sea level is. That's why we have a big wave-cut terrace right now. All of these big rocks that you do the monitoring on, who asked about the big rocks? Those are really durable. I think they're all Santiago Peak volcanics that have eroded from ancient mountains, been in the fan, are very resistant to erosion, and they've rolled downhill. And all the other sediment has just broken apart. So when there was talk of long-term monitoring, I was thinking to myself, well, in the last 30 years, sea level's risen about 3 or 4 inches. Okay? Those rocks, there's a top to them, right? I mean, look at all the, where all your stations are. And so the question I was thinking about is, okay, 3 inches, your average tidal range is maybe 4 feet. That's 48 inches. That's about 6%, the variation. So some of this long-term trends could actually be writing changes in submersion time, where any particular area has about a 6% ballpark, right, increase in average submersion, presuming all things equal, which they never are. Right? None of that's factoring out what the levels are, right? But the challenge with those rocks is there's nowhere for them to go beyond the top of those rocks. You're not in a real, most of those rocks, there's not much good intertidal on the sea cliffs because they erode so quickly. Most of the rocks, most of the intertidal critters, are really on those durable rocks that are out there. So that's something to keep in mind as you're thinking about, the meaning and intent of all this. But the point here is that we know over the last 100 years or so, and this is a combination of tidal gauge records, satellite altimetry, red here for satellites because we haven't had them back in the 1920s. So 23, sea level is rising. There might be something with global warming. I'm sure it's just a conjecture.
Theory.
Just a theory, right? No, we have clear evidence that sea level is rising. It's going to continue to rise. So about 18 centimeters over the last 100 years. There's that uplift rate here locally. And you can see the clear pattern here if you want to think about who's going to win, right? We know who's going to win. It's going to be sea level rise here. It's going to be sea level rise almost everywhere. With a few exceptions that are really weird because actually the land is rising faster because there's a bunch of ice on it in the past. New England. You don't want to lose your house? Move to New England. The sea level's lowering there. So here's what the future holds. These are various projections for sea level rise on various economic models, global economic models. What you don't see is sea level dropping. We've pre-purchased our way out of the next two ice ages with CO2 going in the atmosphere. So, it's going to be sea level rise. It's going to be driving a lot of the challenges you face. I think you're seeing that already. I remember this rock that was here. I'm sure this was an existential crisis for the national park, given their mission. But do we leave this or do we wait for some knucklehead to push it on their friend, right? But that rock used to be pretty stable. When I started bringing my kids here, I never thought that rock, even though I'm a geologist, I'm like, that rock's gonna be there forever. Yeah, got a little assist, I think, with some pneumatic jacks. But the reason was it was literally on the edge. So this is part of the challenge we face today. I can see those changes having been enough. And here's just a projection. This is from a couple years ago now. But tidal flooding, presumed a 5-foot sea level rise. So you don't see it much here around Cabrillo where you see the substation, because that's a pretty vertical wall, right? But if you think about it, what you're doing is concentrating the wave energy even more on the current sea cliffs, right? Because you slowly lift sea level, you're going to be eroding in those sea cliffs even more. So don't park close to the sea cliffs. Okay? So I hope that was helpful. It's a lot of information. I want to make this available to you. Again, what I recommend, Pat Abbott, who's been at SDSU forever, you've seen him on the news. He had a really nice book. If you want to do a deep dive, it's 200 pages, The Rise and Fall of San Diego. It's really the rises of the falls, but I think he simplified it. And then this book, again, From Shore to Sea, the geologic section in there. I'll be happy to share this with you. Oh, that's not the right email. That mail shouldn't be it. But I'll share this with whoever so they can send it out to you, and happy to answer your questions again. Do you have 2 minutes for questions. Almost time that night. I just got 2 more minutes. Okay. Sure.
Conglomerates, what do they have to do with each level, or is it just one?
Yeah, so the conglomerates is a really fancy pants term for big rocks that all got dumped together and left there, right? So if there's a couple places you can find what could arguably be called conglomerates. If you were to preserve this intertidal zone right here, why are all these big rocks sitting here? Because this is where there's a huge amount of energy coming in, right? So it would not be a surprise if you were to find fairly large class of sediment concentrated there. And that's kind of what you see up here. This would be called, I think it would be called a matrix supported conglomerate. Now I'm just showing off, right? Or the other place you can find conglomerates as a depositional sort of feature are in the cross section. Where do you go?
Is it as you drive down?
As you drive down, exactly.
Yeah.
So right here. So these conglomerates you can see, right? They're almost touching each other. This is what we call a clast supported, because they're more touchy-feely. Be trouble this ditch, be careful. So these are sort of what's at the bottom of a channel, just like if you were to go to a stream today, and there was a variety of class out there, different sizes. You'll tend to find the largest class at the lowest part of the stream, because that's where the fastest flow is, right? So the smallest ones that were there, they just continue to get carried away. And I was just thinking, you can have one thing with you, and we can make some of these for you because we haven't stayed. It's a plexiglass tube about this big around, maybe that's all, filled with water and a mix of sediment ranges. And you can shake that thing up, or give it to a kid who needs to get some energy out of shake up, and then let it settle. And it will settle in a graded bed. And you can then hold that right up to some of these layers that's there. Now what you need to do then is expand their mind, literally, to think about a whole pile of sediment coming down and covering the whole area. But the pattern vertically is the same, right? It's a graded bed. Of course, the stuff sets up first. So 2 places you might find conglomerates here. In the intertidal and ancient intertidal, and then in these submarine canyon channels, right? Again, remember, you think of a delta as sediment being dumped down, but some of these flows, like I showed you, are incredibly erosive, right? So they're scouring out in the upper part of the fan. Then they flow out, they lose velocity, and again, all the sediments settle out. Which ones? The coarse ones first. So you tend to lose your big class up there in the upper fan channels. They get there, but there's not sufficient energy to continue to move them out, even though it's downhill. Also, I should say, geologists tend to mess around with scales, vertical and horizontal scales, because these things happen on such long scales. It looks like the fan's like this. We could be talking about just a couple degrees. And that's enough to have these kind of flows.
What about concretions?
So concretions are something very different. They may look like a big clast,
Right.
like these things, but they form within the sediments. The concretions are a geochemical formation. So you may have, and oftentimes, like, how do you form a concretion? Oftentimes, if you were to crack one open, and don't do this because we're in a national park, but if you were to crack one open, you'll see it's kind of concentric, and in the middle, there's maybe something there, right? And oftentimes, how these concretions start is with an organic center, right? It's kind of like a M&M or something. Right, some sort of organic goo, poo, critter, whatever it's got buried, and you have a geochemical redox reaction around it, almost like a three-dimensional sort of sphere, right, leaving the concretion, and you differentially precipitate out chemical materials that form a concretion.
So it has to have water as an intricate.
Almost all concretions are going to have to be formed in some sort of fluid environment.
Now,
And there's different ways they can form.
I read on Mars they found concrete.
Yeah,
So
yeah.
that proves that there was water.
Lots of evidence for water at one point on Mars. Now, it doesn't mean you have to have water to have them stay, right? There's some concretions that you can see right there, and I didn't even talk about those, I should have. But there's some weird sort of, curvy, resistant areas. And the reason you see them is because they're more resistant to erosion than the sediment around them,
Now,
right? So they
some of
weather
the
out.
concretions around Birch Aquarium near the parking lot,
Mhm.
they're magnetic. So is that just
Oh.
iron ore?
You can have iron differentially precipitated out.
Because
Yeah.
I'll take a magnet to it and they all go
Really?
right to the magnet, yeah.
They need street value. Yeah, big magnet. I'll have to check that out next time I'm there.
Yeah,
I did not know that.
the terrace above the aquarium.
Oh, yeah, and the other thing the other place you can also form concretions is actually, wherever you have sufficiently, they can form in soils,
Really?
right? Yeah, but the soils have to have the moisture.
Oh.
So they can actually form paleosols, ancient soils. You can find concretions in them. But the reason they can form is because there was a fluid environment. There was pore water in there
Okay.
that allowed them to form. So I was a little too glib. I shouldn't say they can only form in the ocean. They can form on
They
land.
have to roll around, right?
No, they can form right in place.
Oh, okay.
There are other kinds of spherical things that can roll around and form. These called rhodoliths. They're actually algal.
Okay.
They grow on rocks as they get rolled around. That can sometimes be preserved.
Yeah, I didn't ask that a lot from visitors. How long does it take to make a form of good completion?
Well, that's a great question.
Depends
Longer than they'll be there. That's a really good question, and I'm
on-
not
So
a
many same
geochemist.
questions.
Yeah. Interesting. Because the other thing to keep in mind is they don't form necessarily at the surface. They form in the ancient subsurface, right? That's a good question. I may have to get back to you on that. I'll check with my. I know like things like manganese nodules in the deep ocean. That's like centimeters per million years, kind of like super slow, right? For some of these concretion, I'm not really sure. It's a great question. It may be hard to actually measure it in some cases. Yeah, so I don't have a better constraint.
So it's all classes, is that what
Yeah, I didn't talk much about the source of all these sediments, but we have these volcanic ranges, right? We sort of have the roots of those mountains exposed today. How many of you live over in Del Cerro? Everyone live in sort of the Del Cerro area? There's Santiago Peak Volcanics, that's kind of bluish rock. A lot of what we see exposed farther to the east are really the roots of these ancient mountains. And so all that stuff's been eroded out. So there's a lot been going on. I focused right in on Point Loma. There's a hella complex history for San Diego. That's why I pointed to Pat's 200-page book. That I think is really first order, great layperson coverage if you're really into the rocks.
I've read in his book that the oldest rock is over in Penasquitos in the waterfall.
I wouldn't doubt it. Yeah, I mean, most of what I do is in the deep ocean or an ancient sediment, so ocean drilling cores, looking at climate change way in the past, well, younger than the Cretaceous. Or when someone said Bonnie Becker, I work with Bonnie on skeletal chemistry, so looking at growth history of Mytilus and other critters, trying to understand this thing, because someone brought up, are they old or are they growing slow? Like, that's a fascinating question in biological time. You know, because it could just be that they're all relatively young, right, for the outer limits. Or, energetically, are they growing more slowly? Those are two fundamentally different responses to fundamentally different kinds of things. So those are the two hats I try to wear.
That Cretaceous rock that's in La Jolla, is that an offshoot of our Cretaceous rock here? I mean, did it go down and resurface?
So there's some Cretaceous in La Jolla exposed, no doubt. A lot of those rocks are Eocene, actually younger in age. And part of that reflects the Rose Canyon Fault, right? Because the reason you have, I didn't really talk about this part, but I should probably shut up. If we hop over to that Rose Canyon shot, notice how it takes a sharp left right here?
Yeah.
Mount Soledad and Point Loma are there because of that turn. I think the sense of motion, it's basically like they hit a corner. Now it's not just sliding, it's caught there, and so you're starting to slowly deform the sediment. Think of like a sheet of paper where you start to push it together, parts are going to come up, other parts are going to go down. So north of that, you can see the blue is there, right? You can see right there, there is Cretaceous stuff exposed. But up in this area around La Jolla Shores and such, there's some Cretaceous, but a lot of it's younger material, a lot of it's Eocene. Also, largely fan-based stuff. And this is, again, what Pat is by far and away the expert in. All right, yeah, I'll give it a shot. So I'm happy to answer any questions and hang out for a bit. I know that.
Thank you for giving such a nice presentation. So if you, do you mind if I volunteer you to answer questions during the break?
Yeah, sure.
Sweet, okay. So if you want to continue asking questions, feel free to come on up and ask more questions. For now, we're going to take about, should we make it 10 minutes, Pauline? Okay, let's make a 10-minute break and we'll meet back at 2:05.